Okay, we did a part of equilibrium revision. The magic of this is, especially for shy students, I'm just touching the theory note. I'm not doing that much. But then the difference is when you're going through the note, then you would feel like that I've done everything. That you can refresh your knowledge very easily with this. Okay, so the main purpose of doing this is to give you guys some sort of a little refreshment to go through your note. It's a must that until we did up to unit 11. So each time when you're done with this tutorial book, then you're supposed to go back one round with theory. Then your insight is totally changing. When you understand everything more and more better and better, you see things way clearly once you go through theory after papers. Anyway, I know this is again, I'm just doing a very little, but I know you guys need that little push. Okay, so we're going to talk about these acid-base reactions and everything. But before that, we're going to talk, we did up to here, I guess. Yeah. So this is just a normal condition. I've given these questions. If you are just adding normal acid or normal base just to a normal solution, according to that acidity or basicity, concentration of or the pH of the medium is changing. But these are those questions that I have given just to show you guys that pH is changing. But if it is a buffer solution, even if you add a little amount of acid or little amount of base, pH is not changing. It has a resistivity to pH. Those solutions are called buffer solutions. There are 4 different buffer solutions for your theory, for your syllabus. You're supposed to memorize all these buffer solutions separately for final exam. It is a must that you memorize all these separately. Then I'm going to explain this buffer action. What happened when you are adding a little acid or base? How does it not changing? Okay, this is the main reaction. But in the medium, this is less because this dissociation is weaker. To support that, we are adding externally any of these acid. So this is my example I have taken weak acid and it's sort of strong base. So this is the part actually mainly controlling the pH of the medium. If you add OH minus, so H plus reacting with OH minus, this reaction is moving more and more forward to release more H plus, so that OH minus is reacting with this H plus and control the pH of the medium. If we add H plus to the medium, when you're adding H plus, this reaction is now H plus is high, so this reaction is going to backward. When it is going to backward, H plus is decreasing. But now let's say this is not enough in the medium, but this one is supporting, this is giving, regardless how much H plus we are adding, not only this is also providing H plus to make this acidic, so that H plus is decreasing, so that it is maintaining the pH of the medium. This is the base. Subtle, is that enough? Go through the note. I'm not explaining everything because otherwise we have another like more than 100 to go. Then dilution doesn't do anything because same OH minus and same H plus adding. So pH is not changing during the dilution for buffer solutions. Henderson-Hasselbalch equation we are using to find the pH of the medium. So here I have taken this same example. Sodium acetate dissociate into acetate and sodium. Acetic acid, acetate and H plus. Then there are 2 different conclusions in this Henderson-Hasselbalch equation. One thing is this acid dissociation is very weak. So that C1 minus X equals to C. So that once the dissociation occurs or at the equilibrium, what the acid amount supposed to be equal to the initial acid concentration. And then the other one is this. This becomes the salt concentration. Sorry, this is the salt concentration. But finally, not only this sodium acetate, but also acetic acid is releasing acetate part. So the total acetate is this. But since the dissociation is weaker, since X is very small, C2 plus X equals just C2. So this C2 is this C2. So that we consider salt concentration equals to initial salt concentration. Okay, keeping that in your mind, I'm going to this to derive this. Just write the expression for Ka, then subject H plus, then get the log 10 values of everything. Then log 10 H plus is pH, log 10 Ka is pKa. These two, negative multiply negative become positive. So the acetate comes to the top. This is negative, so that acid goes to the bottom. So C2 plus X equals to C2. So that acetate concentration is the salt concentration. So that instead of acetate, we are just writing here salt concentration. And also here again, initial acid concentration equals equilibrium acid concentration. That's again, X is very, very smaller. So that C1 minus X equals to C1. So that instead of this equilibrium acid concentration, we can write here just acid, initial acid concentration. So that this is become salt and this is become acid. So that we can derive this equation, whatever the way you can get the idea. So salt divided by acid, or salt can be whatever this anion concentration. This is the weak acid HA, or A minus is the conjugate base of the acid. So we can go with conjugate base divided by acid as well. And then another something little that a couple of questions are there, they were asking that way. If the acid salt concentration, these two are equal, this part becomes 0. So that pH equals to pKa, concentrate well. Okay, then Henderson-Hasselbalch equation we can use for to find pOH as well. I'm not going to go through, but you must, it's a must that you're supposed to go through all these, because now they are asking how to derive these during the question. At least one question they are asking. When there is, we already talked about how to find pH or H plus concentration. Only you are having acid. Using initial concentration and Ka, we can find X, then we can find H plus concentration. When you're having only a salt, this is a spectator ion, so that the weaker part is controlling the pH of the medium. So that acetate taking H plus, making the medium basic, so that we can find the OH minus concentration separately. But here again, this is a mixture. Both these together is in the mixture. So this is fully separating, dissociating, and this is partially dissociating. Now the total acetate in the medium become acetate released from salt 0.01 plus acetate dissociate from acid, that is X. But finally, X plus 0.01 become 0.01 because this dissociation of acid is very, very weaker. So here again, I'm showing this, how to derive this one. Then once you derive that, then pH equals pKa. They were given Ka value, get the minus log 10 of Ka, that is pK, you can find that. Then acetate and acidic concentrations, but both plus and minus X are cancelling off. Then the normal way you can find the answer. I'm explaining only up to this. You're supposed to, if you are learning this the very first time. So that is 24 students. It is a must. You are doing everything, like every single theory plus all the questions together. If you are really comfortable with questions, second time, third time, fourth time, when you are reading the note, then you can skip questions. But otherwise, without questions, you are not gaining knowledge. Understand that, Anu? No questions, no knowledge. Okay, I've done a lot of questions. Then blood part, easy, understand. I'm not going to go through. Okay, see, it's very easy for me. Why it's easier? I've done lots of questions. The note has almost like how many pages, but still very few are theory. Okay, sparingly soluble compounds, then this is saturated. Saturated means you cannot add more salt. It is precipitating. Okay, you can get this saturated solution. Then whatever the solid is dissociating into aqueous ions with the stoichiometric ratios, we can write this Kc expression. But you guys know concentration of solid is constant. So that solid constant multiply Kc is the Ksp. So you can derive Ksp. Same as all the other equilibrium constant, this can change only by changing the temperature, otherwise it's constant. There are three different categories depending on how much they dissolve. Very soluble when the concentration is, when the solubility is greater than 0.1. Sparingly soluble when the concentration or the solubility is less than 0.01. In between, slightly soluble, that is in between 0.01 and 0.1. Solution classification, unsaturation, saturation, and supersaturation. I'm going to start from here. This is the normal condition. This is fully saturated mean. Aqueous phase has the maximum ions it can bear. If you add little extra, let's say we are adding a little extra of A or little extra of B, then what happens? The externally added part is precipitating because it cannot keep more. It simply means when this ionic product is greater than Ksp, you're going to get the precipitation. Or the other way around, if it goes this way, now Ksp is greater, so ions are not enough to make the precipitate. So when Ksp is greater than ionic product, ions are less, ions are not enough to make the precipitate, so that it doesn't make a precipitation. Clear that? Supersaturation, saturation. Okay, so initially, when we dissolve, it's dissolving and its dissociation maximum, the maximum concentration with time it's decreasing, comes to some certain point. But precipitation starting from beginning, 0. The saturated aqueous solution is reprecipitating. So that's starting here. Precipitation starting and increasing with time when the saturation is increasing when it comes to saturated. But there is a level that both forward backward equals, that we call it reaching the equilibrium. Supersaturation and calculations. Let's go with the questions. Oh, common ion effect. Common ion effect mean something that you have a little excess in the medium as a common ion, that is a disturbance to equilibrium. So that common ion either can increase or either can decrease the solubility. Okay. How do they increase the solubility? When you are making, simply if I say, when you are making complexes, complex is more soluble and complex is more stable. So that this reaction is moving to forward. So AgCl getting dissolved to give Cl plus and Cl minus. So we are adding little excess sodium chloride to this. And here you are adding, what is the common ion here? Cl minus. So that Cl minus interferes with this Cl minus. That Cl minus is reacting with Cl plus when it is in excess to make this Cl chloride complex. So this is more stable. So that this chlorine is decreasing. So to increase that, reaction is moving forward. So that this is more and more going forward to give extra Cl minus to the medium. So that AgCl is dissolving. Clear that. So solubility increasing. This condition, see, what is a common ion here? Minadi, what is a common ion? Sulfate is a common ion. So, what happened here is, it is making this barium sulfate precipitation. It's not showing there. So, when you are adding sulfate, the first equation, to decrease sulfate, you are going backward, making this more and more barium sulfate precipitation. So it is decreasing the solubility. Questions. Under certain condition, that is under ammonia. So to identify whether it's AgCl, AgPr or AgI, we check the solubility with ammonia. When you are adding ammonia, it is reacting with Cl plus and this complex is more stable. Since this complex is more stable, it is decreasing the Cl plus of the medium. So this reaction is going more and more to backward To increase Cl plus, now this is getting down. To increase that, this reaction is again going to forward. It simply means this dissolution is increasing. Cl bromide and Cl iodide is not for your syllabus. But sometimes this is possible. When you are using this weak acid, part supposed to come from this weak, okay? This supposed to come from weak. Then what happened here is, to this equilibrium mixture, we are adding H plus. Then H plus reacting with phosphates, make this phosphoric acid. What do you know about the phosphoric acid? That's a weak acid. So that dissociation is moving towards this direction. It decreases phosphates. To increase that, reaction goes to forward or right at the same time, so that barium phosphate concentration is increasing or solubility is increasing. Clear that. So addition of a acid increases solubility here. So two different conditions. Okay, when the conjugate base is stronger, it's more acidic. When the conjugate base is weaker, it's less acidic. Clear that. Because see, HI is strong, I minus is weak. I minus weak means this is acting as the conjugate base. Conjugate base definition is this supposed to get H plus. How easily this is getting H plus? Not easily, because this like to exist as H plus plus I minus easily. This H plus getting back to I minus is really harder. Understood? Because this is a strong acid just existing as H plus and I minus in aqueous medium. So that when acid is stronger, conjugate base is weaker. When acid is weaker, conjugate acid is stronger. Why you say, sorry, conjugate base? Why you say this conjugate base is stronger? Because as a base, this is very easy to accept H plus and going back to here. Dissociation is weaker. Summarization, okay? Summarization. I don't feel like you're supposed to do this one because we did all these questions to equilibrium as well, sorry, inorganic as well, but still some equilibrium principles are acting here. When the KSP lowest to highest, okay, concentration gradient increases from here to here, KSP same way increasing from here to here. So that way, from lower KSP to higher KSP, we can precipitate. Or the very first one is this dill HCl. So the dill HCl mean HCl concentration is very, very low. So the compounds and cations which need very low Cl minus concentration is precipitating here. Then to this HCl mixture, once you remove these precipitations, we are adding H2S. Okay, H2S is dissociating to H plus plus S2 minus, let's say aqueous. Okay, so 2H plus plus S2 minus, so that medium is already acidic. So when you are adding acid to this medium, what happens? When you are adding H plus to the medium, now the medium is H plus is high. To decrease that, reaction is going to backward minadi. Then what happened? Reaction is going backward. It is taking subtala. It is taking sulfides as well. It is taking sulfide as well. So that sulfide concentration is less. So that here, which need less sulfide concentration, which is having low KSV is precipitating. Rather going to group 3, I'm going to group 4 now because in group 4, we are adding ammonium. The medium has ammonium hydroxide, medium is basic. So we are adding OH minus to the medium. OH minus gets away with this H plus. So reaction is going to which direction? To increase H plus, this reaction is going to forward. When it is going to forward, this is more and more dissociating to give sulfides to the medium. Now the sulfide concentration of the medium is greater, so that cations which need more sulfide concentration is precipitating. Okay, now that is the equilibrium principle. Okay, next one is this condition. Here we separate them as hydroxide, so that we are adding ammonium hydroxide. This is dissociating again to NH4 plus OH minus. Okay, but when OH minus is greater, all these gives hydroxides. These are hydroxides, and magnesium hydroxide also hydroxide. Those are precipitates. So to avoid that higher hydroxide concentration to this medium, we are adding NH4Cl. NH4Cl. Now this is acting as what? This is acting as NH4 plus acting as common ion. Common ion. As a common ion, it increases NH4 plus. But this doesn't like that. This want to have reach its own equilibrium. So this is trying to decrease that. So to decrease that, this reaction is going to left direction. When it is going with hydroxide. So that hydroxide concentration is now less. So that less hydroxide concentration needed for these cations so that they get precipitated. Understood? Rest of the part we did for inorganic. See how easy the equilibrium lab is. Equilibrium lab is very easier. To determine this KSP value of calcium hydroxide, we're going to do a couple of these questions, essay questions. I'm not going to skip any of these questions. Okay, so we are making the saturated solution. How do you make sure it is saturated? That solid supposed to be remain here. Then we know it's saturated. Then we're going to get a portion of this out. Then titrate. Calcium hydroxide dissociate into calcium 2 plus and 2OH minus. Stoichiometric ratio is X is to 2X. If you find 2X, 2X equals hydroxide concentration. Okay, this is hydroxide concentration. Then X is calcium 2 plus concentration. Then KSP become, since this is to the power 2. You have 2 here. So then the KSP equals 4X to the power 3. If you know X, then we can find KSP. So we're going to do this little titration with HCl, then get the number of moles of HCl, which equals to number of moles of OH. Then from that we can find X, then from that we can find KSP. Clear that? I'm just going with the refreshment, okay? Not everything I'm explaining here. How many questions you guys done? Convinced yourself. I have done questions that nobody ever do. OMG. I guess. And see, these are the part that I given these connections of these different equilibrium constants. That's all with third book. It's that easy. But that book has how many pages? 190? 136. Yeah, let's say 39. Like, yeah, 50-page book. Let's finish this today. The revision part. Okay. Saptal, are you okay? Okay. Dhoni? Just listen. That's why I'm asking. That's why I'm asking you. I'm gonna mute this, and I don't want this to spread with people because I'm not blaming to anybody, or I'm not coming from Colombo gives you the best, because I have all these experience, and like even I tell you that's, yeah, I told, like, you know, the one of these parents were talking me like class here, and she has 2 season 1 test. What's the point wasting how much time in a boarding place and everything, going back and forth, and how much she is tiring then. You can do that. Anyway, moving to the first equilibrium, there are 2 different types. Minadi, try to concentrate well. Tell me, how did you grab this? Because others have theory, you don't have theory. Okay, heterogeneous mean these 2 different phases. 2 different phases. When you are using 2 phases, different phases, heterogeneous. Homo mean 1 single phase, liquid, liquid, gas, gas, aqueous, aqueous. Okay, the first part, we are going with the heterogeneous phase equilibrium. Let's say that we have a glass here filled with water, and until the last drop of water is evaporating, this is just evaporating water because it's not covered. Okay, let's say we have water here, but still we are covering this with a lid here. So after a particular time, it is starting to evaporate, but after a particular time, this is concentrate with moisture. It cannot concentrate more with vapor, water vapor. So it is giving extra water vapor back. Then it is reaching this equilibrium of liquid water and water vapor. That is the first equilibrium that we are talking about. That is the evaporation of liquid in a closed container. So initially, whatever it is, that you have this condition, this, let's say this surface area from the top to the bottom is same, not this kind of a glass kind of a containers we are using in the laboratory. Those are beakers, or everywhere the perimeter is same. Okay, then this surface area is constant. Here the surface area constant. Here the surface area still constant. So you are constantly with the same speed you are evaporating. So that initial rate is still exactly the same, and the this is the evaporation rate. It is same, and then this precipitation or this condensation. So the condensation rate is initially 0. Initially there is no vapor here to condense. When it is concentrating more and more, saturating more and more, it is coming down. So that the condensation starting from the beginning, at a particular time, it is reaching to the maximum, and it is getting same rate as the forward reaction, which is evaporation. When evaporation and condensation become equal, that we say it is reaching the equilibrium. That is the condition we are talking about. Then saturated. What is the meaning of saturation? Saturation means the maximum molecules that can exist inside the vapor phase. That is the saturation. Then the boiling point. When, okay, even you heat or even you not heat, this is evaporating. Then this is coming to the saturation very slowly. But if you heat this continuously with higher temperature, this pressure increases really rapidly. And when since this is pushing, now we are increasing the kinetic energy of these molecules forcefully. So more and more molecules are reaching here, and it's starting to bubbling. At the same time, now the pressure is really high here. When the pressure is getting increased and increased, that's the time that this pressure is equal to the external pressure. When the internal pressure equals to the external pressure, we say that is the boiling point of that liquid. Understood? Have you done this? No. Are you understanding? Yes. Yeah, these are very easy. Okay. So when temperature is lower, we need inside pressure is less. So we need to boil to a lower temperature to make it boil when the pressure is lower. Okay, then when the pressure is really high, see, inside pressure high, then we have to boil to a higher temperature to reach that pressure for boiling. So that's what happened in pressure cooker. Okay, that is the boiling graph. Then here, this little thingy, I did a lot in, you have all the short notes I've given. Especially Deepna, she praised so much about this short note. She talked to you, isn't it? Saptarano? I told you, I guess. She came to serve me like there was, I don't remember whatever the class, and she said everything to that class, whatever the class was there. she said those organic inorganic short notes are like so much supporting, and she was keeping a couple of these photocopies, one in the vehicle, one in her bedroom, one in the study place, one in the pantry or somewhere, I guess. Whenever she's passing through, she's just reading it once and just she's leaving there and she's gone. So without effort, then you can memorize everything. Those are, you have all the organic and inorganic. And I don't have time right now, but I'm going to make one for this to maybe 2025 students. Yeah, because I know this organic and inorganic one are really, really supportive to students. If you don't have, you can ask them, or you can just WhatsApp me. Okay, I'll send those. It's a must that you remember each and every single thing on these short notes. Those are not like the larger note became to smaller note, making a short note. Those are like different version of organic chemistry and inorganic chemistry. So another way you are memorizing points. In that, I've explained different phenomenon, how we compare these boiling points, and because metallic bond strength is different, ionic is different, this is covalent. If compounds are covalent, we compare these intermolecular interactions. This is metallic primary, so this is always really high, this is mercury, this is mercury. And all these are covalent compounds depending on Van der Waal and London, and then hydrogen bonding, so on. Whatever the intermolecular strength is increasing order, exactly the same way the boiling point is also increasing. And this is a normal boiling point, that is 1 atm or 100 kilopascal. Okay, I'm going to use this one just to save time. Let's say that we have vapor here. So the temperature is 20. At 20, it's a vapor. So when we pressurize here, since molecules are getting closer, they can make more intermolecular interactions, so they can liquefy. So that liquefied system, we boil again. When we boil again, this is evaporating. So this is going to this vapor phase again. Now again at 30, at 20 you have the liquid, but at 30 again you have this vapor. At 30, again I am pressurizing. So that part is liquefying, or the whole thing is liquefying. This mixture, now I am heating back to 35 degrees Celsius. Then this liquid part is evaporating. Liquid part is evaporating. Now again we have the vapor. Apsara, are you okay? Now I'm pressurizing again. At this pressure, Pabasara, this is not liquefying. Why? Explain more. I don't want to work. What is the reason this is not liquefying back? You cannot liquefy. Because 35 is, let's say this is a gas, helium kind of a gas. So 35 temperature is really, really high for it. So Saptala, its kinetic energy is now really high. Even you make these molecules very closer, they are not making intermolecular interactions, so they are not liquefying back. That temperature that we cannot liquefy using whatever the pressure, that temperature is called the critical temperature. That pressure is called the critical pressure. 1 mole of that substance volume is called critical volume. Clear that? Okay. This graph, they would never ask you to draw this one, and they would never ask you to explain how you're going to draw this. They are considering these points. Okay, Menadi, you may feeling little confused here, but we are just drawing the graph, and this is the solid, and this is the liquid, and this is vapor. I'm just giving the graph. Okay, you don't have any idea. Then this equilibrium. What is this equilibrium, Menadi? Well done. Well done. What is this equilibrium? Liquid vapor, then you guys know this equilibrium is solid liquid. That is the first thing. And the second thing, from when you are going always from here to here to this side, see the temperature is increasing. When the temperature is increasing, okay, let's say we are going here, when the temperature is increasing. Now the pressure is constant. So see, first you meet solid, then you meet this whole part is liquid, and then you meet this whole part is vapor. See, phase transition going from solid, more heating liquid, more heating to vapor. Okay, then the other way around. I'm going to go this kind of a point. Then initially, this part is at very, very low pressure. What do you see here? Very, very low pressure, you would see vapor. When you increase pressure, when you add more and more pressure, vapor start to condense. So this part is liquid. Understood? Then when you pressure more and more, molecules get more and more closer. So you are now here now. Now you are in solid state. Okay, going from more compact to less compact, always entropy increasing. Going from more compact to less compact, you are breaking into molecular interactions so that you have to support energy for that. So that always enthalpy is plus. See, always entropy, enthalpy of all these three are plus. Melting, freezing, vaporization, condensation, sublimation, deposition. And then that you can see with these three, solid, liquid, and vapor, all these three are in one single equilibrium. Triple versus equilibrium, triple point. This is a critical point. Up to here, even when you heat, you can liquefy when you increase the pressure. But beyond this point, whatever the pressure you are given, when you increase the temperature beyond this point, you cannot liquefy this. So this is beyond this one, you have a condition which is having both gas and liquids together. You call that mixture supercritical fluid. Temperature and pressure above which a gas cannot liquefy, which is called the critical point. Critical pressure, critical temperature. 1 mole volume is critical volume. That's what they are asking. This is temperature, x-axis. This is pressure, y-axis. Minadi, are you understanding this? Really? Oh, everybody? Oh, cool. And a little part is doing for unit 4 as well. Yeah. Okay, these are the three that I have explained, the temperature and pressure variations. This is for water. What happens with water is when you pressurize, the lowest pressure, you have the vapor. But when you increase pressure, you are going to solid. When you increase pressure more and more, so this part, see, you are going to vapor, because when you increase more and more pressure, molecules are more and more closer. The vapor molecules are very, very apart from each other. Then the next condition for water is ice, because ice trapped with hydrogen bonding, trapping with this air bubble. So when ice are condensing more and more, ice is making liquid. Because of that reason, this TB line is negative, has a negative slope. This is only for water. If you have a negative slope in exam, you should know that is about water. Positive slope is for everything else. And another condition that they are giving is this carbon dioxide. Here the critical point is here. At the critical point, pressure is 5.1. But see all these other conditions, this is the critical point that is less than room pressure or 1 atm, but here it's greater. So that at 1 atm, you are on this line. On this line, condition goes with vapor and solid. So that's why hard ice or dry ice or solid carbon dioxide goes from solid to vapor phase transition at room temperature. It doesn't have melting point at room temperature. When you dissolve, okay, A is volatile. A in its own condition, on only A is existing here. So it is evaporating to its maximum. So the maximum vaporization for the saturated vapor pressure. At that time, it has its own boiling point. Then let's say we are mixing this A with B, but B is non-volatile. So they are making interactions here. So B doesn't let A to evaporate freely. So here the vapor pressure of A is less. So this is called partial pressure, which is less than saturated vapor pressure. So this is greater and this is less. Clear? Because non-volatile solute decrease volatility. Okay. See the next condition. That condition is that. Just memorize non-volatile decrease volatility. Then volatile condition. This is separately evaporating. And this is also separately evaporating. These two together now contribute to make this pressure here, so that the here pressure, total pressure, is always greater than this separated pressures. So that this total pressure is always greater than this. And at the same time, total pressure is also contributing from A's and B's both pressures, so that these two pressures separately is smaller, because together it's greater. Together they are making the pressure, so that these two pressures are always less comparing to separate saturated vapor pressures. Understood? Ideal solution. When any compound having its own intermolecular interaction separately, when you mix these two together, they are when they are in one single container, still they have the same interaction. So that then you call it a ideal solution. What is ideal gas? What is ideal gas? No intermolecular interactions. No volume. No collisions are perfectly elastic. Yeah. No chemical reaction is okay, but no marks because you have to go with definition. Okay, that is ideal gases, but this is ideal solution. Raoult's law comes to ideal solution. Raoult's law says partial pressure equals saturated vapor pressure multiply molar fraction of molar fraction of which phase? Liquid phase, molar fraction of liquid phase. Okay, now what is the Dalton's law of partial pressure? PA equals PT into molar fraction of gas phase. Molar fraction of gas phase. How do you prove this? To prove that you are using two different conditions. To prove that you are using rate constants. Okay. Initial reaction is this, forward reaction is this side. This is a reactant. So we are writing rate expression to the reactant A liquid. A liquid is proportional to molar fraction of A. You can prove that. So that instead of this A liquid, I'm writing this expression again, K prime into XA or molar fraction of A. Backward reaction, this is a reactant, A gas. So you can write A gas concentration with respect to, Donnie, have you done 11? Yeah, finish. So that backward reaction rate equals rate constant into A gas concentration. But A gas concentration we are not counting on because A is a gas. With gases, we are going with the pressures. So that instead of concentration, you can write backward reaction rate equals to K into partial pressure of A. See, forward reaction, backward reaction, at equilibrium, these two are supposed to be same. So that I'm writing RF equals RB, so that I can write, getting these two equilibrium constant to one single here, PA equals K into XA. These two together I'm going to get as K. So very simple. This is, I think they were given to derive this thingy in 2020 or so. 19 or 2020. Yeah, this is the thingy they were given. That's why I'm asking you guys to concentrate after 2019. Before 2019, they never asked directly theory. So that then, let's say if this equals to 1, if this is 1, if let's say only XA is presenting, what's supposed to be happen with the P, partial pressure of A. This is becomes saturated vapor pressure. Only A is in the medium. It is fully saturated. So that is the saturated vapor pressure. So that instead of this PA, okay, then this become 1. Then I can write this PA equals to P naught A, which also equals to K. Because this is 1. If this is 1, PA equals K equals P naught A. So K equals P naught A. So that instead of K here, I'm writing P naught A here to derive this little equation. We can write same thing for PB as well. Then this is the second version of Raoult's law. Relative wave pressure depression of one component equals molar fraction of the other component in liquid phase. Okay, this is the partial pressure in the mixture A and B together. But that's always less than saturated vapor pressure of that, because when you are with the second one, that together make the total pressure. So each pressure contribution from each component is less. That's why what we have shown here. See? See? P naught A is always greater than PA. So PA is less. P naught A, or the saturated amount, is always greater. So that if you get the difference between these two, that is called vapor pressure. Since it is decreasing, we call it the vapor pressure depression. Vapor pressure depression. And that vapor pressure depression, if we divide by the saturated vapor pressure depression divided by the saturated vapor pressure, we call it relative vapor pressure depression. Relative vapor pressure depression. See, the relative vapor pressure depression of one component equals molar fraction of the other component in liquid phase. This is the second law of Raoult's. Understood? These are really easy. These are really easy. This one is again really easy. See, this is the Dalton's law of partial pressure. PA equals Vt into Ya. That Ya is the molar fraction of the gas phase. I'm going to subject Ya, which equals PA divided by P total. But according to Raoult's law, what is PA, Professor? Yeah, equals to what according to Raoult's law? Yeah, XA. So then this is P naught A into XA. What is the P total according to Dalton's law, Minadi? According to Dalton's law, P total equals P A plus P B. But PA is P naught A XA. PB is P naught B XB. How easy? Equilibrium life is extremely easy if you concentrate well. If equilibrium life is harder, if you don't have enough knowledge of this unit 3, unit 6, or otherwise, if you are not concentrating enough. Then the qualities are asking these characteristics of ideal solutions. There is no mixing energy, and then volume is not changing other than the volume changing of this discontinuous nature of the matter. So you have to memorize this. You have to memorize. They have same intermolecular interactions. So we consider them as ideal mixtures. Then we're going to come to this one. For that, I'm using this one. So this is a Raoult's law. See, PA equals P naught A XA. When the temperature is constant, always it is saturating to one single pressure, that is called the saturated vapor pressure, to that temperature, which is a constant. So P naught A is constant. So PA constant XA become Y equals MX. So M is the gradient which has this constant increasement. Okay, so When maximum A is in the medium, that pressure is called saturated vapor pressure. So we can draw this for two different compounds, not only one. Okay, so this is for XA. So PA is increasing up to maximum. So this is maximum pressure, that is P naught A. Then molar fraction is going from 0 to 1. Then I'm going to draw using this axis. I'm going to draw this P naught B. See the P naught B maximum. When the P naught B maximum, that value equals to 1, molar fraction equals to 1. Then you have the highest vapor pressure, that is the saturated vapor pressure. So in the mixture, always the total pressure goes in between these two, because that's always equals to PA plus PB. So it's always in between P naught A and P naught B. Is this clear? When you learn theory, it's going to be really easier now. Everybody, I guess okay. Okay, so that is that. But you don't have exact connection to composition temperature. It's always a downward facing curve. There is no direct relationship. Non-ideal. Ideal means same interactions. Non-ideal mean interactions are not same. Interactions can be greater or less. Let's say when they are together, their interactions are greater. Minadi, I want you to answer. Now the interactions are greater. When the interactions are greater here, now here the interactions are greater. Can they operate more? No. Great interactions mean you are bound into liquid phase. So less evaporation. So less evaporation. Clear that. When the vapor pressure is less evaporation mean vapor pressure is less. You're gonna go get a wash your face. When less molecules are here, less vapor pressure, so that we call it negative deviation. Pressure less negative, but that happen when interactions are high. Interactions are greater. Understood? Then what is the positive deviation, Minadi? Intermolecular interaction is supposed to be less. Then more and more molecules are going to vapor phase. Then pressure is high. We call it positive deviation. That's negative deviation and positive deviation. The rest of the part you can understand easily. So this reaction is a negative deviation. Yeah, negative deviation is exothermic. Positive deviation is endothermic. You can read the rest of the part, but you have to memorize these sets of these reagents for negative and positive deviation. You have to memorize, but still see something more I want to show you guys. See, whenever you are drawing a tangent or the contact line, whenever you're drawing the contact line, that you cannot see upper or lower separate limits, upper or lower. But if you go with this one, see, when you come to this position, from here to here, this is getting down. From here to here, this is getting down. So that is simply mean this one has a maximum point, and also here, this one has a minimum point. So that if you have a higher maximum or higher minimum, higher maximum mean large positive deviation. Higher minimum mean large negative deviation, large positive and large negative. Those are the two differences. Just see when you're again drawing this one with the temperature, see if you go with this one. So if whenever you are drawing these contact line, you cannot go with the negative and with the minimum or maximum. But if you draw here, see from here to here it's decreasing, here to here decreasing, you have a minimum and maximum points. These are with boiling points. Okay, this one, exactly same phase diagrams. This is important to go with this fraction distillation. So when you're going at pressure, at low pressure, you have a gas. When you're pressurizing more and more intermolecular interactions, they are coming to liquid. But with temperature, when you have the lower temperature, less kinetic energy, so that molecular movements are restricting, so you are existing as a liquid. But when you increase more and more pressure, more kinetic energy, more easily they are going to gas phase, so that you have a vapor. Rest of the part, we're going to do a question, so you're going to understand that. Read everything. Okay. This one, they says, when you're doing this, if one compound is volatile, by increasing the temperature, you can just separate the volatile one. This is a thermometer. Then when you use a condenser, that volatile one to condense again, then you can separate. But let's say that you have 2 volatile compounds, 3 volatile compounds. What would you do? Then you're supposed to go with some sort of a series of fractional distillation. Here, this is the fractional distillation one. You have to go with series of simple distillation. So each of these beads consider as one simple distillation. This is one distillation, second distillation, third distillation, and so on. So whenever you are distillating, more volatile one are going more and more to vapor phase, less volatile one are coming down back to colliding with beads, coming back to liquid phase. When the temperature is exactly to the boiling point of the separating one, it is existing here as a gas. Then again, it is going through this path. Then using this condenser, we can separate that again as a liquid. Clear that? Okay, for that, to understand that, I'm showing this little thingy. Let's say initially we have Minadi. Initially we have this mixture 50 and 50. A50, B50. Finally, A80, B20. Which one is more volatile? A is more volatile. Okay, see, A is more volatile. Now what do? We separate this part, condense it. Now we have the liquid. Now we heat again. Who's going to vapor phase more? A going to vapor phase more. Now A is increasing little by little by little. We do this continuously until we get POA separated. This is called the fractional distillation. And the harder part is to understand this one, but it is not harder. Okay, so the very first mixture that the composition is 50, we are boiling here. When we are heating here, when we heat here, when we are heating here, temperature of the mixture is little by little increasing. Finally, it starts to boil. What is that? That is a boiling point of the mixture. So, get the parallel line to x-axis that you can get the boiling point. That you can get the boiling point. Okay. Then, that's the boiling point. But still, we don't want the boiling point. We want this vapor to get separated. This is a liquid curve. This is a liquid side, liquid side. Then the vapor side is supposed to be the other side. So this is a vapor. Then I'm going to come up to here. Then I'm going to hit the vapor curve. This point has the maximum vapor. So I'm going to cool the vapor. See, the temperature is going down and down and down. When it is cooling, now I'm going to get into this liquid. That liquid is the one I gotten from this one. So it has this 80:20 composition. That one again I'm heating. Boiling, this is a boiling point. Then collecting the vapor, condensation, cooling down. I have the liquid. Boiling again, this is the boiling point. Then this boiled one, I'm collecting the vapor, going down and down and down until I separate this POA from here. Clear that? Little more to go. And a little more to go. Okay, how do we find the composition? Initially, we had XA and XB. It's evaporating to YA and YB. According to Raoult's law is right into this part. PA equals V naught XA, PB equals V naught BXB. That's the Raoult's law. Then Dalton's law of partial pressure goes to this part. PA equals total pressure into YA, mean this vapor pressure of vapor phase. PB is PT into YB. YB is the partial pressure. Sorry, not the vapor pressure. Molar fraction of A is YA. Molar fraction of B is YB. But anyway, whatever the way we calculated these partial pressures, these two partial pressures are supposed to be equal because you have one single system and only A and B components. So that 1 equals to 3. 1 equals to 3. So we can write that. And then 2 equals to 4. 2 equals to 4. So we can write the second equation. Then subject YA and YB, which equals P naught XA into P naught BX. Now I'm going to the second distillation. This is the first distillation. Now I'm moving to the second distillation. Going from this, I'm going to separate this YA and YB, which is in the vapor phase. Now I'm going to condense and put it again back to the titration, to the fractional distillation flask. Okay. So now this is YA and YB. Those two again evaporate to give YA prime and YB prime. See, total pressure is the pressure of these two together. Now I'm going back with the same calculation. So PA equals P naught A, but now you have YA here. P naught B, now you have YB here. This is the vapor phase. So that I can write for vapor phase according to Dalton's law. PA equals PT into YA prime. PB equals PT into YB prime. I'm going to again, this one PA, this same PA equals to each other. Then this PB and this PB same. So I can equalize them. Then I divide 1 by 1. I come here. Then YA prime divided by YB prime equals P naught A, P naught B, this part, multiply YA divide YB. But YA divide YB equals this. Are you guys feeling sleepy? Don't be sleepy. I know you are not doing anything. I'm only talking. Don't be sleepy. Be inspired and you will be sleepy. YA divided by YB equals P naught XA divided by P naught B XB. So that instead of this YA and YB, I'm writing P naught XA into P naught BX. Then I have P naught A and P naught A here, P naught A squared. P naught B and P naught B multiplicity, P naught B squared. It simply means then XA and XB. Whatever the times I'm distillating, whatever the time is the power of XA divided by XB. So N power gives P naught A, P naught B divided N power into XA divided by XB. Clear this. Applications easy. Memorize. Questions. Question takes time. See how much questions we have done, how much knowledge in your brain. That's why I want you guys to just move to the next part, steam distillation. Steam distillation is going to compounds which are immiscible. Immiscible means they are not mixing with each other. Drink little water if you feel little sleepy or something. Professor, are you okay? Sleepy? I guess yes. Yeah, I know. When I'm just talking, you guys are not doing anything. Little more to go, just maybe 5-10 minutes. Okay, then I know this is happening every time I'm doing the revision because I'm doing a little faster. You have to concentrate really well. If you get sleepy, you're missing something. Go with the recording again. When you're having A separately, that is P naught A. B water separately, that is P naught water. And when you are mixing these two are not mixing with each other. Let's say oil and water, not mixing. So that these two are operating independently from each other. So Dalton's law of partial pressure, we are writing this way. This time, this P naught A is the P naught H2O is a P H2O. Exactly same. So that we can come up with this condition. Total pressure comes from the saturated vapor pressure of components. Saturated vapor pressure. And then this is 10. This is 10. This is 7. This is 3. So 10 is greater than 7. So that PT is greater than P naught A. And also, if we cut this one, 10 is greater than 3. So that PT is greater than PH2O. If the pressure is greater, what happened to the boiling point? Less temperature is supposed to be given to increase the pressure because pressure is already high. So that the boiling point is less. sorry, so that this is the other way around. This one coming from this. So the mixture's boiling point is now less than boiling point of water because the pressure is the other way around. Pressure high mean boiling point less. Understood? No? Okay. That is when it is, listen, inside the pressure cooker, you understood is correct. There, to make the pressure outside pressure, inside pressure to outside pressure, when you are heating, you have to heat to higher temperature. Understood? It's not that pressure is increasing by itself. By the temperature, we are increasing the pressure. But here, Dhoni, see what happened here is, now you have this mixture. Okay, let's say another one is here. This is more volatile. Let's say volatility of A is greater than B. This is giving more pressure here. But this is giving less pressure. Who need more temperature to make this pressure to outside temperature, outside pressure? This is A, this is B. Yeah, we need B to heat more because it needs to make more vapor. Understood? So that when inside pressure is higher, you need less temperature to boil. Clear that? So that less temperature comparing to both the boiling points of these two, but oil's boiling point is really high. So this is boiling less than the temperature of water. So less than 100. That is the steam distillation theory principle. Understood? Okay, so that we can separate any of these compounds through the steam distillation to boiling less than 100 degrees Celsius. So we can save its qualities. It's not thermally decomposing. That is the use of that. Then we can derive this little equation for steam distillation. Raoult's law for miscible, mixing compounds. Steam distillation is for immiscible, not mixing. Okay, so you can come up with this little equation. Their molar ratio equals to saturated vapor pressure ratios. Molar ratio equals to saturated vapor pressure ratio. This setup advantages are here. I'll skip this. Just read. I'll explain only this one. This is again another equilibrium constant. That is the, here the difference is, if you use carbon dioxide, can you write this one? O2 aqueous, can you just write CO2 aqueous, PO2? You cannot because CO2 aqueous is not existing. What is existing? Carbonic acid. So this condition is only for oxygen they are using. Concentration of oxygen and the partial pressure of oxygen. That ratio is called the Hendrix constant. Okay. KD is for homogeneous. You have two different liquids. Again, when you see two different liquids, water and let's say carbon tetrachloride, I2 is dissolving in both. Then I2 dissolution in aqueous and I2 dissolution in organic is different. So that they're going to have an equilibrium condition here. So same I2. I2 here, but the medium is different. Between them, you can make this equilibrium that is called the distribution coefficient, sorry, distribution equilibrium constant, KD, which is the concentration of one single thing, but in two different, requirements, you can read that. Okay. Last one is the solid extraction. Saptal, I remember this theory. Do you remember this theory? Come. We've done this earlier lots of time, but now we are not doing this because we need to save timing. Come, darling. I want you to talk to this one. So she's taught. She's short. I guess. Yeah, she can. Everybody can hear this. Okay. So I need to explain. Yes, explain. Explain that if you go more and more smaller portions, extraction becomes the calculation. So, okay, who are these? I've done presentations in front of hundreds of people, and in front of my, that's the hardest, in front of my supervisor, because she's always giving me the hard time asking me questions. So the 1,000 people are better than my supervisor. I'm getting really nervous. I need to get this huge preparation for that. Hey, my PhD preparation. I just want to make sure that how much you understood, how much you memorized. Thank you. No, she's nervous. Otherwise, I know she can do that. I don't want to say, I don't want to waste time. She's trying to petting with me. Otherwise, it's not hard for you. I know that. Anyway, okay. Now, let's say that we extracted this essential oil using any other method. Using fractional distillation, sorry, steam distillation, we extracted an oil, but still it's not that pure. So we want to separate that oil in a pure state. Let's say it is more soluble in ether than in water. Then what we are doing is we are mixing that compound with ether. So the compound is more soluble in ether, mean it is going more and more to the ether phase when you shake water ether mixture. Then once you evaporate ether, you can only separate this compound. Then let's say initially we had 1 gram of compound. X is going to the vapor as ether phase. So the how much remaining in water phase is 1 minus X. Clear that? Okay. Then let's see what is the percentage of that. To get that, we need KD. When you are writing KD, whatever the A in organic phase or ether, whatever the A in aqueous phase. Okay. KD they were given. So X is the mass in organic phase. So the remaining become 1 minus X because we were initially using 1 gram. We were initially using 1 gram. But here we can play with grams, masses, because this is concentration. So that mass divided by molar mass is the number of moles. That divided by volume is the concentration. So we divide with molar mass and then we divide with volumes. So that I'm not going to go with volumes for now. Let's say 100 milliliter of water mixture, 100 milliliter of ether. So this is cancelling off, only X is remaining, cross multiplication. So we can find X. For 1 grams, 5 portions out of 6 has extracted. So the percentage is 83.33. Okay, this is as a whole, we were using the whole ether 100 cubic centimeters. Let's see if we divide that ether into 2 different portions of 50 cubic centimeters, then what's going to happen? Okay, now let's say again, X amount is going to ether layer. 1 minus X is remaining aqueous layer. This time again, molar mass is the same, but now the volume is different. Here it's 50, here it's 100. So that when you do the calculation, now X is 5/7. Then remaining in aqueous phase is how much? 7/7 minus 5/7 equals 2/7. This is remaining in the aqueous layer. To this mixture, Minadi, now I'm adding the rest of the 50 cubic centimeter. Now, how much initial I have? Earlier, initially I had 1, then remaining is 1 minus X, but now initially instead of 1, now I have 2/7. Let's say Y is extracting to ether layer, so remaining become 2 divided by 2/7 minus Y. Let's say y is in the ether layer. If you simplify this one, then you're going to get this answer, y equals 10 divided by 49. In the first portion, you separated 5 over 7. From the second portion, you separated 10 divided 49. If you add these two together, you can get how much extracted from same 100 cubic centimeter of ether, but using two different attempts. That is 45 divided by 49. If you go with the percentage, that is 91.8. But earlier, it's 83.33. See, the efficiency is increasing when you are using smaller portions. Okay, you can go with like 10 to 5 four times or 10 into 5 times and so on. Each time you would see that the amount extracted is increasing. So this sort of a calculation is really, really frustrating, going with the first extraction, second extraction, third extraction, and fourth extraction. So we are using this little trick for that. If the remaining is this amount, after nth extraction, remaining become a over b to the power n, and n is the number of extractions. Clear that. We have a couple of questions in theory note as well. Sorry, in our tute. A little more, I think, is there, I guess. Is that all? Finish. Yes. Equilibrium is that easy. Equilibrium is that easy. To understand principles, I did like infinity question. That's why I want you guys to go through the note and with all those questions. And it's the path is really effective. Otherwise, these students cannot reach 100 marks for chemistry. They've done it many times now. When the very first time Punsala done that, I thought that's her talent. Seriously, I never thought that it's my path that I did that. I thought in her body, like talent. That's what I thought. I thought she has the talent, she's doing that. Then the rest of the years, when they're saying, ma'am, I have 49 out of 50, 50 out of 50, then I understood that is this path. You trust the path that you can do this. All right, done with this refreshment.